Okay, so we're going to take some notes today about gas stoichiometry, and we're also going to talk about the ideal gas law. And it looks like PV equals nRT, where R is a constant, P is pressure, V is volume, N is number of moles, and of course, T is temperature. R is a constant that requires us to use consistent units, and its value is 0.08206. And its units are liters times atmospheres, that's the volume times the pressure unit, over moles times Kelvin. So N is moles, of course, and T, temperature, always has to be in Kelvin when you're working with gases. The ideal gas law only applies to ideal gases, but we're going to make the assumption that that's what we're working with. And it can be used to derive all of the other equations, because if you take PV equals nRT and solve it for R, you know that any set of P times V over N times T is equal to any other set. And we already talked about how the combined gas law contains Boyles Law, Charles' Law, Gay-Lussac's Law, and so on. So, you can find number of moles using PV equals nRT, of course. You can even solve this equation, this big equation, for number of moles, either N1 or N2. And of course, using number of moles, we can determine the mass of a sample if we know what the gas is. You know, if you have 2 moles of oxygen gas, you know that would weigh 64 grams, right? It's 32 grams for 1 mole. If you have 2 moles, it would be 64. We can determine how much of a gas is needed for a reaction. We can determine how much of a gaseous product is produced. We can do limiting reactant questions. We can do percent yield. So we can add gas volume into any of our previous stoichiometry type problems. So now we've got something that looks like this. You should be very familiar with mass of A to moles of A to moles of B to mass of B, of course, and you also learned how to go to liquid volume of A and B if we're using molarity. If you know moles, you can find liters. And we talked about using, going from moles to liters of a gas at STP. Well, now we don't have to be talking about standard temperature and pressure. We can change the temperature and pressure and use PV equals nRT to find out moles or any of the other variables. And of course, you should remember, 22.4 liters is 1 mole of any gas at standard temperature and pressure. So you can memorize it, or if you forget, you can always say, well, PV equals nRT, how many liters is that? V equals nRT over P. And so what's the volume when the number of moles is 1? R is always 0.08206. The temperature at standard temperature is 273 Kelvin, and the pressure is 1 atmosphere. And when you divide this, when you do the math, you should get 22.4 liters. And it says stop here for today, but we're not going to stop just yet. So R can have, remember we said it has the value 0.08206, and that is liters, atmospheres per mole Kelvin. So moles and Kelvin go on the bottom of the fraction. But because there are so many different units for pressure, there are different values that you can use for R. So if you want to use these values for R, you don't have to convert the pressure to atmospheres. But a lot of people will convert all their pressures to atmospheres quickly before starting a problem with the ideal gas law. So you can do it either way, but here's one with liters and kilopascals per mole Kelvin. Here's 1 liters bars per Kelvin per mole, and so on and so forth. So you can use any of these numbers in place of R. You'll notice these last 2 are the same because, of course, millimeters of mercury and torr are the same thing. Oops. Okay, Molar mass. We know what molar mass is. It's grams per mole. You find it on the periodic table. It can be sometimes abbreviated capital M. Of course, we already have capital M for molarity, so that can be a little confusing. But if we have a gas at a fixed temperature, pressure, and volume, we can find the number of moles pretty easily using the ideal gas law. If we know the number of moles and also the mass of the sample, we can find the molar mass of the sample, which is cool because that helps us identify the substance. So the mass is equal to the number of moles times the grams per mole, right? You can find the mass. And so to find the number, if you can find the molar mass, for example, then you can know what the gas is. Let's say, for example, you find that you have a gas that's 32 grams per mole. Which gas is it? Probably oxygen. If it's 28 grams per mole, it's probably nitrogen, N2, right? And gas density is something we can also calculate using these ideas. It varies according to temperature and pressure and volume. The density of the gas in the atmosphere is really important because as a mass of air heats up, it's going to expand because it can, it's not contained. And as it expands, its density is going to drop. And an air mass with a low density will move upward in the atmosphere. You say heat rises, right? But it's really air masses that rise. And it's really not so much that the air mass rises itself, but that cooler air masses around them will drop in underneath and push them up. So this is really important for weather and air circulation on the planet, and for other things too, like determining how your car behaves in the winter versus in the summer. If the air is warm versus cool, that makes a big difference in terms of how much oxygen is getting into the engine for that combustion reaction. So you know D equals M over V, mass over volume, and you also know that mass is equal to the number of moles times the molar mass, right? And if we solve that for N, you have little m over big M, right? And if you plug that into PV equals nRT, it's looking kind of complicated, but it's not too bad because here's our little m over big M right here. That's N. PV equals little m RT mass, RT, over molar mass. And if you solve that equation for density, that means you're going to keep the mass on the top and get the volume on the bottom. It looks like this. M over V, mass over volume, is equal to molar mass times pressure over R, which is a constant, times the temperature. So you can, determine gas density using this equation. So this is one that you might want to write down as well. Little m over V equals big M times P over RT. Okay, so we're going to talk a little bit about how molecules move and how fast they move and all of that. So we talked about the fact that we have to use the Kelvin scale when we're talking about temperatures, and I wanted to discuss why that is. The reason is because the Kelvin temperature system is directly proportional to the average kinetic energy of a gas particle. So when we heat a gas, the particles have more kinetic energy. Well, you already knew that when you heat something up, its particles move faster. But I want to talk about where the Kelvin scale comes from. So it comes from this. If we take a balloon, and you can try this at home if you want, take a balloon and measure its circumference, and then you can estimate its volume from that, and then you put it in the freezer, you find that it gets smaller. So what we've done is we've plotted some points that correspond to a balloon at this temperature has this volume. And as we decrease the temperature, it has lower volume and lower temperature and lower volume, and so on and so forth. We've gotten some samples of gas to be really, really cold. And we find that it's really obvious. For sure, the colder the sample gets, the smaller its volume gets. The issue is, we're not sure what happens when you get temperatures that are extremely, extremely cold. Actually, we've created some very, very cold samples, very close to this point, but we've never actually gotten there. But we can extrapolate down. And theoretically, this point is 0 Kelvin. We call it absolute zero. Zero. So the colder the particles get, the slower they move, and eventually it might be possible to make them stop. And when they do, the particles won't take up any space. They'll have zero volume, except for the volume of the particles themselves, right? Now, the reason that we have never actually gotten a sample to absolute zero is this. If you have two particles with different speeds, this particle's moving really fast, it's bouncing around in the container, and this one's moving slower. If these two collide, there's an energy transfer. Energy from the fast particle goes into the slower particle, and it speeds up a little bit, and this particle slows down. So you take this one that got sped up, and you take it out, and you find another slow particle that's really cold, and it hits and releases some of its energy. And you keep doing that over and over. The trick is, if you have a particle moving very slowly, and you want to cool it down and slow it even more, you have to find something that's colder than it, with slower moving particles than it, to take some of its energy away. And if you can find something colder than absolute zero, that's moving less than not moving at all, then you could cool something down to absolute zero. So it really can't be done. But we've gotten pretty close. We've gotten very cold temperatures. So we created the Kelvin scale so that if you double the temperature, let's say from 100 Kelvin to 200 Kelvin, then you should be directly proportionally doubling the volume. This only works for the Kelvin scale, though. The Fahrenheit and Celsius scale don't work. The Kelvin scale is a shift from the Celsius scale. The difference between 1 and 2 on the Kelvin scale is the same size of a temperature change as the difference between 1 and 2 on the Celsius scale. So it's just the same thing, only shifted. So, 273 Kelvin, this is 0 degrees C. So the reason the Celsius scale does not work with gases at all is because if you're saying that you have a gas at 0 degrees Celsius and it can be cooled down further, does that mean its particles are going backwards? No, of course not. It means its particles are going slower. At 0, the particles are not stopped. So when you're working with gases, you always have to use the Kelvin scale. So if you're given numbers in Celsius, just add 273 to them to get the Kelvin scale. Now, if the question asks you to answer in Celsius, then you got to convert it back into Celsius by subtracting 273. Okay, let's talk about diffusion and effusion. These are processes based on the way particles move around in a gas. Diffusion is the process by which one gas mixes with another or spreads out within a room. For example, you can try this little experiment at home. You can try it with a few different people at your house. So let's say you got a hallway. Well, you got 3 people in the hallway and you open a container of perfume or something that has an odor. Maybe you peel an orange or something like that. The gas particles will spread out and they'll move through the room and they'll bounce off of all the particles of gas that are already in the room, the nitrogen and oxygen and argon and all of that, in your air. And eventually you'll start to see, people will notice that odor. And if you try the experiment, what you usually see, of course, it depends on if you have a stuffy nose or not and how good your sense of smell is and all of that. what you usually see is this person is going to notice first, and then this person is going to notice, and then this person is going to notice. And effusion is the process in which a gas escapes from a container. So if you are spraying a perfume here, then watching how it diffuses, that's one thing. But if you take the lid off the perfume and you don't spray it at all, you still might smell it eventually because gases will come out of a container. Another application for effusion that you're probably familiar with is if you have a typical latex balloon with helium inside of it. That helium stays in there and it keeps the balloon floating in the air. But after a few days or maybe a week, it doesn't float so well. The next thing you know, it's sitting on the ground. Well, the only reason that could be is if some of the helium left and some air got in. So helium will escape from the container. It'll go right through the little pores in the latex because helium is a really small gas and the particles are very tiny. It's monatomic, right? And the gas will just go out of the balloon. So how particles escape, there's a rule, there's a law, there's an equation we can use to discuss how these particles move. And the equation, and this is for an extra credit problem on the test. You don't even have to do this for the test if you don't want to. The equation looks like this. The rate of escape of particle 1, substance 1, maybe helium, over the rate of escape of substance 2 is equal to the square root of the molar mass of substance 2 over the molar mass of substance 1. So that's an equation that you might want to write down. And again, there's an extra credit problem related to it on the notes or on the test. It's not something you have to worry about too much. But there is an interesting use for this. Back when we were first starting to build nuclear weapons, they used Graham's law for separating uranium-235 from uranium-238. You'll recognize those little numbers as the mass number, right? So uranium-235 is lighter. Well, uranium's a metal. It's not going to be a gas at room temperature, but if you react it with fluorine, you can get uranium hexafluoride, UF6, right? And that would be a gas. And UF6, if the atoms of uranium are the 238 variety, they're heavier, they're slower, and they will effuse out of a container through a porous barrier more slowly. And then uranium-235 will get picked up on the outside of that container. That's an interesting use for that, I think. Okay, there's one other equation that I wanted to show you, and I don't have a good PowerPoint for that, so I'm just going to draw this one out. It's really, really simple. It's the simplest equation you're going to see in a chemistry class, but there's a little bit that you got to think about. This one is called Dalton's Law. Of partial pressures. Dalton's law of partial pressures. So, Dalton's law of partial pressures comes from John Dalton. You remember him for the Dalton model of the atom. And essentially the law looks like this. Let's say you have a balloon and it's got a mixture of gases in it. So this is a law for mixtures of gases in a container. This particular balloon has helium, oxygen, and CO2 in the balloon. And the total pressure inside the balloon, let's say we measured it, it's 5 atmospheres. And we want to know where those 5 atmospheres come from. Well, obviously they come from these particles bouncing around off of each other and hitting the walls of the container. And they're pushing outward, and they're going to end up with some pressure caused by the total amount of the gas. Well, each of these gases is going to contribute some portion of the pressure, and each of them have their own what we call partial pressure. Part of the pressure comes from each of the 3 gases. So to figure out how much each gas is going to push outward, Well, what really is the most important thing to look at is how many particles of gas there are for each of the different types of gas. And if you look at this picture, you should be able to see, I hope you can see this well, the light blue helium is obviously the most prevalent. So let's say you had a question that said the total pressure in a balloon was 5 atmospheres, and helium's pressure was 3 atmospheres. Its partial pressure, the pressure that it's exerting on the container. And CO2's partial pressure is 1 atmosphere. What's the partial pressure contributed by oxygen? And to solve the problem, you'd say, well, 5 is equal to the sum of each of the pressures. 5 is equal to 3 from the helium, plus 1 from the CO2, plus 1 something from the oxygen. So what's the answer? Well, it is 1, right? So Dalton's law of partial pressures looks like this. Total pressure equals pressure from gas 1 plus the pressure of gas 2. I should say partial pressure of gas 1, partial pressure of gas 2, plus the partial pressure of gas 3 plus, and we put some dots to say there could be many other gases involved as well. Normally, when you're working with air, you're going to have a mixture of gases, right? So there's an interesting application for this. And this is something that I would like for us to do in the lab. We're going to try to simulate it here soon in the lab. Mrs. Kaczynski actually went in and did this lab for you, and you're going to be able to use her data, and hopefully that'll work for you. But I wanted to show you why partial pressures are really important in the lab situation. And then maybe at the end, if I remember, I'll tell you an interesting story about partial pressure as well. If you are doing a reaction in the classroom, and you've got this gas, or you've got this flask here, and let's say you've got some HCl or something like that, and you're reacting it with zinc. It's going to be a single replacement reaction, and the product you're going to get is zinc chloride and hydrogen gas. So we're getting hydrogen gas that's coming out the top. And when it comes up and out of the liquid, of course you'd see bubbles down here in your flask. But as it comes out of the liquid, if you wanted to measure how much hydrogen you were getting, what are you going to do? Well, you could maybe put a balloon on the top and it would fill up the balloon, right? But hydrogen won't be the only gas in there. You'll have hydrogen, but remember there was already air in this flask. So you would have hydrogen being produced, but also air. And then how are you going to get the gas out of the balloon? So sometimes collecting a gas from a reaction is really tricky, and scientists have found kind of a cool way to deal with this. It's fairly simple. So what you do is you take your flask and you make sure you've got a lot of your reaction going on so that there's not very much air at the top. So here's your zinc, here's your stuff, your HCl, you're bubbling up some gas, and then you're going to put a stopper in here with an opening, and that tube is going to come out and your gas is going to come out. Now at first, of course, you're going to get some air with it too, so you want to let it go for a little while, and then you would maybe start to collect the gas at this point. Now, how are you going to collect the gas in a container that doesn't have air in it and in a way that it won't explode? Collecting gases can be tricky like that, right? So what we do is we take this tube and we put it down into a container of water. So now the gas is going to come up as little bubbles, right? Well, in order to capture those bubbles, what we do is we take another container, often a graduated cylinder, because then you can have a measurement, right? fill it totally with water. Lay it down inside the sink or the container of water that you're using here. And then you pull it up so that it's upside down in your stream of water, your stream of bubbles. And there's water at the very, very top. Because you can take you tried this when you were little in the bathtub probably, but maybe you forgot, so try this in your kitchen sink. If you take a glass and you submerge it in a sink full of water, and then you turn it bottom side of the glass up, and you lift it up, you can pull a bunch of water all the way up. You'll have a big water column here until you open it up and let gas come in. And then when you lift it up and air comes in, then all the water falls out. Maybe it's been a while since you've done this, but you've done it before. So here we have gas bubbles coming up, and they end up filling up this top portion with just gas. Of course, it's the bottom of the graduated cylinder, but it looks like the top, right? It's upside down. So as you fill it up with gas, this water level moves down and moves down, and eventually you have a section in your graduated cylinder of gas and a section of water. And you can put your thumb over it and flip it up, and then the water goes to the bottom and your gas is on top. And now you've captured your gas, and you can cap it and keep it for later if you'd like. There's a couple of issues. First of all, this column of water pulling down on this gas will create a lower pressure. So in order to make sure that the pressure of this gas is the pressure of the air around it, which you can look up on the Weather Channel website, because air pressure changes all the time, but we keep track of it pretty well. In order to make sure that this gas's pressure is equal to air pressure, you want to wait until the water level is even with the water level out here, so that the amount of pressure the air is putting here is the same as the amount of pressure that the gas is putting here. So you just move it so that it's lined up right. The other issue is, if we look at this gas sample here, so I'm gonna make a blow up of this, okay? If you look at that sample, you're gonna see, hopefully you got all the air out, and you just should have, remember we said we were gonna make this H2, okay? So you should just have H2 particles in there, except, you know how water evaporates even when it's not reaching the boiling point? On hot days it evaporates faster, and on cold days it evaporates slower, but it still evaporates, right? Well, at the surface of this water here, there's going to be some evaporation, and that evaporation is going to get into here. So in our gas, we've got mostly the gas we want, but also some water vapor. Of course, this is our hydrogen. So we know the pressure outside, right? It's equal to the air pressure. We know the pressure inside the gas, I should say, is equal to the outside air pressure. And that's equal to the pressure of the hydrogen plus the pressure of the water vapor. That's Dalton's Law, right? There's only two gases involved, but we know that the total pressure is equal to the sum of the two pressures. Well, we want to know this pressure, because if we know its volume and we know its pressure and we know its temperature, then we can figure out how many moles of it we have. So how are we going to find this pressure? We know the outside pressure. We want this pressure, so we have to know this pressure. And this pressure, water pressure, the vapor pressure of the water, is determined by the temperature of the water. And if you can figure out the temperature of the water, you can look up on a chart what the vapor pressure of that water is. So it sounds kind of complicated, but you're going to look up this one. You're going to look up this one. So these two you just look up based on, this one is based on temperature. This one's based on weather. And then you can figure out the pressure of the hydrogen or whatever gas it is you collected. In the lab that Mrs. Kaczynski is going to show you, she's going to be collecting gas out of a cigarette lighter. Don't smoke, but if you have extra cigarette lighters, you can donate them to chemistry teachers because this lab is a nice, fun one to do. And it's a much better use of them. The one other interesting place where partial pressure shows up is in your bloodstream. So in your blood, which is a liquid, right? There are different gases dissolved in your blood, right? So there's oxygen gas, there's carbon dioxide gas, and the amount of oxygen gas and carbon dioxide gas that are dissolved in your blood in different parts of your body determine whether oxygen leaves your bloodstream and goes out to your cells, maybe to do cellular respiration, or comes into your bloodstream. If the partial pressure of oxygen is low, then oxygen is usually taken in by your bloodstream, and that would happen in your lungs. So if you want to become a doctor, you'll be learning a lot about partial pressures of gases in liquids, which is kind of strange, but it's kind of interesting, I think. All right, we'll stop there.